In this video, we're going to be introducing the idea of the derivative and talk about how it relates to slopes. So if we recall, the idea of slope just represents the rise over the run or the change in our y values over the change in our x values. This is a topic that we learned all the way back in Algebra 1 and is prominent through all of mathematics, even through calculus. So another name for slope, right? Another name for slope that we often will see is average rate of change. They mean the same thing. So average rate of change just represents the slope of a secant line, So if you recall, the secant line is just a line that goes through our curve at two different points. And so if we find the slope of that line, that's just what we call the average rate of change of our function over that interval from a to x. Now, sometimes they'll use fancy notation like this. This is delta y over delta x. It just means change in y over change in x. And this thing right here is really just our slope again, right? It's just the slope. This is our y2, right? This is our y2. We see that in our y coordinate of our second point here. This is our x2. We see that in our x coordinate of our second point there, right? And then we have our y1. F of a is y1. And we see that in our first point there, while a is just our x sub 1 and is the x coordinate in our first point there. So this quotient that we have right here is the same as just the slope. Now we're told that x cannot equal a, because if x is equal to a, the denominator is 0, and we have an undefined value. So when we're talking about average rate of change, we talk about, generally it's just talking about the slope of our line or of our secant line going through our curve. Now, let's take a look at what happens when we have, so here's a diagram. What happens when this point gets closer to a, when x and a converge on each other, right? So as x gets closer to a, and you can see how far apart x and a are here, when x gets closer to a, take a look at the slope of our secant line here. So in red, we have graphed a tangent line to our curve at the point a. So as x is getting closer to a, notice that the value of our slope of our secant line is kind of approaching the slope of that tangent line. And we can see that the secant line is getting closer and closer and closer to actually becoming that tangent line. But what happens when x equals a? Well, when x equals a, the distance between them is 0, and we see that our slope is undefined. So we actually can't find the slope of a secant line when x is equal to a. But it seems like that should be what we want if we're trying to find the slope at a itself, at the tangent line, right? So the slope of the tangent line seems to be what we want if we're looking at x getting closer and closer to a, and actually when x is equal to a, it looks like it turns into our tangent line, but we have an undefined slope there. So if the slope is undefined because our denominator is equal to 0, what can we do to figure out how to find this slope at our tangent line? Because we know in order to find the slope of a tangent or the slope of any line, we generally need 2 points. So how would we find this slope? So that brings us to the problem of the tangent line. So a tangent line, by definition, is just the limit of our average rate of change of our secant line, right? So basically, you take the limit as x approaches a. So as x is getting closer and closer and closer to a, the limit of this average rate of change is representing the slope of our tangent line. So really, a tangent, when we talk about a tangent line, the tangent just represents a slope, right? So the tangent just represents a slope. So when you hear something called this idea of the slope of our tangent line, or this is also the idea of the derivative, right? So the derivative just represents a slope of our tangent line. So it's really just the slope of the tangent line. And that's how a tangent line is formally defined, right? We kind of informally define a tangent as a line that kind of just touches a curve at a single point. That's not the best way, because if you have something like this where it kind of just goes through like this, yeah, sure, it just touches it at a single point. But a better way to describe a tangent line informally is it's where a slope just touches our tangent, or where the line just touches our curve at a single point and follows the trend of our curve. So it kind of has the same slope of our curve. So if we're looking at this quotient here, this quotient, when we take the limit as x approaches a, we can see kind of what we were looking at here, right? As x is getting closer to a, it appears that our slope here is trending toward the slope of our tangent line. And so by using limits, we can show that the same is going to happen if I were to go from the other side. And since those values are equal, then we can say that that limit is just the value of our tangent. So looking at the next slide, we can see that we have this alternative definition for the derivative. So the first definition that we looked at is great if we're trying to find the value of the derivative at a single point that we're given. Whereas this expression here, right, we call this the difference quotient, f of x plus h minus f of x all divided by h. So we use the difference quotient if we're trying to find a more general expression to represent the slope of our curve. Right, so this is used to find basically like an equation for our derivative. So when we're talking about derivatives, remember, the derivative is just the slope of our tangent line. So you'll see the word derivative, it means just the slope of our tangent line. It also can sometimes be used as instantaneous rate of change. If you hear the word instantaneous rate of change, that is, again, just talking about the slope of our tangent line at some given point. So the process of finding the derivative, we call that differentiation. So if you're trying to find the derivative of some function, we're differentiating our function. Now, let's look at a couple notations. So there are some different notations that can be used when we're trying to differentiate or when you're trying to take the derivative. These first three, f prime of x, dy dx, and y prime, these actually denote the derivative itself. This represents the derivative itself. The next two here are talking about the process of differentiation. So we use this, so we say d dx of f. So we're taking the derivative of f, or this is the derivative with respect to x of y. So the derivative with respect to x of our function. This right here just means this is the derivative of our function. So the first three represents the derivative itself. These ones are basically telling you to take the derivative. So just keep that in mind when you're considering these different notations. So let's go ahead and take a look at the process of finding the derivative. So we want to find the slope of the tangent line. Remember, this is just the derivative. This is just the derivative. Find the slope of the tangent line of the graph of f of x equals x squared minus 2 at some given point. So we said if we're looking for the slope at a given point, that's where we want to use this version of our derivative. That's where we want to use this version of our derivative. So we'll find f of x, f of a, divided by x minus a, and evaluate there. So we're trying to find it at the point negative 3, 7. So this, right, is at when x is negative 3. This is our value of a here. That's our value of a there. So we want to find this derivative when a is equal to 3. So what is the slope of our tangent line? So the slope of our tangent line is equal to the limit as x approaches a of f of x minus f of a all divided by x minus a. So let's go ahead and substitute in what we know. So we know f of x is this function here. So it's the limit as x approaches a, we said is negative 3. So it's f of x, which is x squared minus 2, minus f of a. So if I plug negative 3 in, negative 3 squared is 9. 9 minus 2 is 7, so it's going to be minus 7, all divided by x minus a negative a, so that's going to be plus 3. Okay, so simplifying the numerator, we get the limit as x approaches negative 3 of x squared minus 9, all divided by x plus 3. Now, if I try to plug in negative 3 here, that's going to give me a problem. I'm going to get a 0 over 0, which we know is indeterminate form. So using what we know from the last chapter in evaluating limits, we can simplify this. We can simplify this by factoring the numerator. So we have the limit as x approaches negative 3 of x plus 3 times x minus 3, all divided by x plus 3. So now we have this x plus 3 in the numerator and denominator that can cancel. And we can then just evaluate our limit with direct substitution. So plug in my negative 3, and I'm going to get negative 3 minus 3, which is negative 6. So the slope of the tangent line is equal to negative 6 at x equals negative 3, or at the point negative 3, 7. So that would be how you would find the slope of our tangent line at that curve, when you're of our curve at that given point. So when you're given a point and you're given your function, this is a good form to use. But if you're asked to do something like this, where it says find the derivative and you're not told what point to find it at, that would be where you would use the alternative version of our derivative. The alternative version of our derivative requires us to use something called the difference quotient. So this piece right here is just the difference quotient. It also just represents the slope of our tangent line. And this is the y coordinate. This is y sub 2. This is y sub 1. This is actually the difference of x sub 2 and x sub 1, right? So x sub 2 would be x plus h, and then x sub 1 would be x. And when we take their difference, the x's cancel and they just give us h. Right, so you can see in something like this, if we have p of x, comma f of x, and q represents x plus h and f of x plus h, if I were to take x plus h minus x, I would just get h. So h is the same as x minus a, right? And we can look at what's happening as the value of as q approaches p, right? So in this, we can see that our slope is getting closer as h gets to 0. And again, we get that undefined value when the average rate of change, right, when the x minus a, or when h becomes 0, because we get a denominator of 0. But we can see that it looks like our average rate of change of our slope of our tangent line is, of our secant line is approaching that of our tangent line. And the same would be true if we're coming from the other direction, right? As I'm getting closer and closer and closer to h being 0 from the other direction, it's getting closer and closer to the value of the slope of our tangent line. So when you're using this, this gives us a more general equation basically for our derivative that you can then plug in values of x for to find the derivative at that given point after that. So let's go ahead and get back into that example. So this is asking us to find the derivative, and it's asking us to find the general derivative not at a specific point. So that would be where we use the alternative method. So we'll call this f prime. So we'll say f prime of x. So the derivative is equal to the limit as h approaches 0. Remember, it's f of x plus h minus f of x, all divided by, well, x plus h minus x, which just turns out to be h. So substitute in x plus h into this, and we can do our substituting and simplifying. So the limit as h approaches 0, x plus h in here is 4 times the quantity x plus h squared minus 5 times the quantity x plus h. So this right here is f of x plus h, and we're subtracting f of x from that, which is 4x squared minus 5x. All of this is being divided by h. Okay, so let's do a little bit of simplifying here. If I were to distribute my negative through, I'm going to get a negative 4x squared plus 5x. X squared plus h expands to be x plus h quantity squared expands to be x squared plus 2xh plus h squared. That's all being multiplied by 4, so let's go ahead and just do that. So that's going to be 4x squared plus 8xh plus 4h squared, right? So that was just the 4 times x squared plus 2xh plus h squared from expanding this here. And then it's going to be minus 5x minus 5h. Oh, running out of space. And then we're subtracting that from it. Okay, so if we combine our like terms, what do we get? Well, this 4x squared and that 4x squared cancel. This negative 5x and that 5x cancel. And we're left with the limit as h approaches 0 of 8xh plus 4h squared minus 5h, all divided by h. Now, what's nice is all of these have a factor of h, so I can factor that out. And I get the limit as h approaches 0 of h times 8x plus 4h minus 5 divided by h. And those h's can cancel, which then allows me to use direct substitution and plug in. So if I plug in h being 0, what I'm left with is 8x plus 4 times 0, which is 0, so that's going to be a 0 there, minus 5. So the derivative, f prime of x, is equal to 8x minus 5. So basically this equation is a general equation for the slope of our tangent line at any point x. So if we know a value of x that we want to calculate the slope of our tangent line, we can just plug in that value of x and it will give us the slope of our tangent line at that point, which is pretty nice. And actually is something that we need for part B. Because if I'm trying to find the equation, right, anytime I see this, equation of a tangent line, anytime I need an equation of a line, that automatically tells me I need a point and I need a slope. Now remember, the derivative is just a slope of our tangent line. So I can find the slope by evaluating f prime at negative 2. And negative 2 is already half of our point. So I can find the y-coordinate by just plugging x back into my original function. So what is f of negative 2? F of negative 2 is, so negative 2 squared, that's positive 4 times 4 is 16. Negative 5 times negative 2 is positive 10, giving me 26. So that's the point there. And then my slope would be my value of my derivative at negative 2. So plugging in negative 2, that's 8 times negative 2 minus 5. So negative 16 minus 5 is negative 21. So this tells me that my slope is negative 21. And if I want to put this all together to write my equation, so I use point slope form, y minus the y-coordinate, which is 26, equals my slope, negative 21, times x minus my x-coordinate. My x-coordinate is negative, so it ends up adding 2. So that would be my equation of my tangent line at x equals 2. For this example, it's asking me to find the equation of the tangent line to the curve of f of x when x has the given value, so when x is 25. So again, when we're trying to find the equation of a tangent line, that means I need a point and my slope. So to find my slope of my tangent line, I need to find the derivative of f of x, and then I would find the point by plugging in x equals 25. So let's find f of 25 first. So what is f of 25? What's the value of my function when at 25? Well, that's the square root of 25 plus 1, which is 5 plus 1, so it's 6. So we have the point 25 comma 6, and we need to find the slope so that we can write our equation in our point slope form. So what is f prime of x? F prime of x is equal to the limit as h approaches 0 of f of x plus h. So that'd be plugging x plus h in here. So that's the square root of x plus h plus 1 minus f of x, which is exactly just square root of x plus h, or sorry, square root of x plus 1, all divided by h. Now when I distribute this negative through, the 1 and the negative 1 are going to cancel because they're going to be opposites here. And I'm left with the square root of x plus h minus the square root of x. And if I want to simplify this, I need to rationalize. I need to rationalize by multiplying top and bottom by the conjugate of what I'm left with in my numerator. So I'm going to multiply by the square root of x plus h plus the square root of x on top and bottom. Square root of x plus h plus square root of x, and that's going to give me the limit as h approaches 0 of, so x square root of x plus h times square root of x plus h is just x plus h. The middle terms are going to cancel. Square root of x times square root of x, their opposite signs, is going to give me negative x. All of that's going to be divided by h times the square root of x plus h plus the square root of x. We get some canceling that happens here. The x and its opposite cancel, and then actually this h cancels with the h in the denominator, leaving me with just a 1 in my numerator. And now that means I can evaluate at h equals 0 because I'm not going to get 0 over 0. So if I plug in 0 for this, I get that f prime of x is going to equal 1 over the square root of x plus 0 plus the square root of x, which is just square root of x plus square root of x, or 1 over 2 times the square root of x. So this is my derivative, and I need to find my derivative at x equals 25. So what is f prime of 25? And I would get 1 over 2 times the square root of 25. So 1 over 2 times 5 is 1/10. So that would be my slope. We could have used the this is the alternative method. We could have used the first method because we're given an x value, and you would have gotten the same result of 1/10. But I wanted to find the general equation and evaluate there. So my equation of my line would be y minus our y coordinate, so it's minus 6, equals my slope, which is 1/10, times x minus my x coordinate of 25. So that would be my equation of my tangent line. So in this equation, or in this problem, it's asking us to find the derivative with respect to x. There is no value of, the derivative with respect to t. There is no value of t that I know that I am looking for. So I have to use the general, find a general equation. So I have to use the alternative form of this. So I'm going to call this, so I'm going to use the dy dx notation. So dy dx, actually it's dy dt. We're taking the derivative with respect to t. It's equal to the limit as h approaches 0 of f of, this time it's going to be t plus h, so it's 1 over 2 times t plus h quantity squared minus 1 over 2t squared, so f of t, all over h. Now in order to simplify this, I need to multiply by the common denominator in the numerator. So that's going to be 2t squared times 2 times the quantity t plus h, quantity squared. Multiply top and bottom by that. So that's actually going to be, let me fix this a little bit. So that's going to be like a 4t squared times that quantity. So if I were to distribute this in, take this and distribute it into this first term, the 2 times the quantity t plus h squared is going to cancel with this, and it's just going to leave me with the 2t squared. So I have the limit as h approaches 0 of 2t squared minus, when I multiply the second one in, the 2t squared is going to cancel with the 2t squared here. So it's going to be minus 2 times t plus h quantity squared. All of this divided by 4t squared h times, I'm going to leave the bottom one ungrouped like that. I'm going to leave it factored in this form. So let's expand the top because I think we'll get some simplifying that will be nice. So if I expand this, this is 2 times t squared plus 2th plus h squared. Distributing the negative 2 through is going to give me this. So the limit as h approaches 0 of 2t squared minus 2t squared minus 4th, because this is a negative 2, right? Minus 2h squared, all divided by h. All divided by h. Okay, so what cancels? So we get 2t squared and 2t squared cancel, and we're left with this. We can factor, right? We can factor out an h from the top, and that's going to leave us with the limit as h approaches 0 of h times negative 4t minus 2h all over 4, oh, whoops, this is not right. Sorry, this should not just be h, this should be this whole thing down here. 4t squared h times t plus h quantity squared. So that's what we're going to have again. 4t squared h times t plus h quantity squared. And then this h here is going to cancel with this h. And now we're not going to get 0 over 0 when we plug in. So let's go ahead and plug in 0. Plug in 0 for h, and I get negative 4t in my numerator. This turns out to be 4t squared times t plus h. So t plus 0 is just t, and that's being squared. So we have 4t to the 4th and then a negative 4t. So that can simplify a little bit. The 4's will cancel, and then this t can cancel with one of these, leaving me with negative 1 over t to the 3rd. Negative 1 over t to the 3rd. So our derivative, dy dt, is equal to negative 1 over t to the 3rd power. So that would be the derivative of this function with respect to t.